This is Saritha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. Today's session I am going to explain about KL transform. So this KL transform is also called as Hotelling transform. So what is the use of transform means it when we are applying the transformation function, it converts the one form of into another form. So this is basically we are using in our image processing. So in image processing, we are applying the transformation means the image is converted into one domain into another domain, that is f of x comma y. We are applying the transformation function, then our output is a capital F of u comma v. So in this KL transform is a reversible linear transformation. So that is explores the statistical properties of a vector representation. So in this KL transform, we are applying here kth image. So kth consider the kth image. So this KL transform is nothing but principal component analysis. Principal component analysis. So we are applying the transformation function on these components. For this case, we are considering eigenvalues and vector values. So we are using here eigenvalues and vector values. The basic functions of the KL transform are orthogonal eigenvector of the covariance matrix of a data set. Covariance matrix of a data set. Here the matrix representation. Of the KL transform. The KL transform here it is P lambda I equals to 0. So in here the matrix representation of the KL transform here P minus lambda I equals to 0. Here in this we are using eigenvalues, and here eigen and vector values. Here I is the identity matrix. Here, the KL transform optimally decorrelates the input data, and after KL transform, most of the energy of the transformation coefficients is concentrated within the first few components. So, no need to consider the total eigenvalues. We can arrange the descending order of all eigenvalues without considering of the all values. So, we can apply the transformation function on when we are arranging the eigenvalues in a descending order, then analyze the entire image. We are applying the scale transformation with few components. First on few components. This is the energy compaction property of a KL transform. So here KL transform, the basic property of this KL transform, it is concentrated. It is concentrated with the first few components. It is concentrated on first few components. For that case, we can arrange the all eigenvalues in a descending order. All eigenvalues are arranged in a descending order and concentrated on a few components. So with use of this one energy compaction property of a KL transform. Here, the KL transform is also known as Hotelling transform or eigenvector transform. It basically works on the principle of principal component analysis. Because of the KL transform. This KL transform more focus on the few components, first few components. It concentrated on first few components of the image. Then it is a statistical properties of the image. It is a statistical properties of the image and has several important properties. It has several important properties that makes it useful for image processing, particularly for image compression. So this KL transform is basically used for image processing. For image, we are using in our image processing for compression. This KL transform basically useful for image processing, particularly for image compression. So what is mean by image compression? We can reduce the data bits. If we are transmitting the information in our digital communication, we are transmitting the information in the form of in the form of in a digital form. For example, if we are using 1000 bits for example, if we are using the compression technique, in this compression we are having different types of techniques. With the use of the scale transform, we can reduce the image size. So we can reduce the image size means now instead of 1000 bits, the image is reduced means we required only 500 bits. So like that, with the use of KL transform is more suitable in our useful for our image processing. Particularly in our image processing, we are having segmentation, enhancement, compression. So different techniques are, but we are using in compression only. We are using this KL transform for image compression only. And the main purpose of image compression is to store the image in fewer bits as compared to original image. So now data from neighboring pixels in an image are highly correlated. It is highly correlated because of this KL transform is basically consider few components of the entire image. Means here principal component analysis, it focused or concentrated on few components of the image. Because of here, compared to original data, here the main purpose of the image compression is to reduce the reduce the bits. So reduce the number of bits we are using for transmission. So we can reduce the number of bits in original image. So the main purpose of image compression is to store the image in fewer bits as compared to original image. Now data from neighboring pixels in an image are highly correlated. Here, in this more image compression can be achieved by image compression is nothing but the size of the image is reduced, the utilization of bits is also reduced. Means it can be achieved with the use of KL transform. In that KL transform, it is achieved by decorrelating the data. So the KL transform does the task of decorrelating the data, thus facilitating higher degree of compression, gives higher degree of compression. And here four major steps. So four major steps in order to find the KL transforms. So what are the four steps here? First one. So find the mean vector. Find the mean vector and covariance matrix of the given image. First find the matrix. Here of x 0 0. Here find the covariance matrix x m comma n. So first find the image and find the eigenvalue and the eigenvector of the covariance matrix. So from this matrix, find the eigenvalues and then the eigenvectors of the covariance matrix. And third one, create the transformation matrix. That is X such that rows of T are eigenvectors. And find the KL transforms. So how to find the KL transform equation? So for this case, what is the in generally we are representing y equal to a into x minus mx. So in this case of y transpose, so both side a transpose a equals to a into a transpose here x minus mx. So from this equation, y a transpose equals to a into a transpose means 1 here x minus mx. From this, x equals to our transformation equation for KL transform, x equals to y a transpose plus mx. So this is the transformation equation for the KL transform. So here consider the image. So here we are representing x002 and xmn. So this is the image. So the image first point is consider the image. That image we are representing here x equals to x002 xmn. Next find the here x2, x0, x1, x2 to up to xn. Here find the mean vector and covariance matrix of the given image x. So now the image is broken down to column vector as x00 to x0 comma n. So here x1 we are writing x00 to xm comma n here. In this the mean vector. So the mean vector is found out shown in below, that is mx equals to e of x. This is the equation 1 here. Mx equals to e of x. This is equation number 1, where e of x is the expected value. E of x is the expected value. N is number of columns. Here we are representing n is number of columns. The covariance of the vector we are representing with x. So covariance we are representing with x equals to cx. Then cx equals to e of x minus mx and x minus mx dash. So this is equation number 2. So first equation we are representing mx equals to e of x, and the covariance we are representing cx equals to e of x minus mx and x minus mx transpose. Here the covariance for the vector, here n is representing the number. Here covariance x equals to 1 by n, k equals to 0 to 1 to n, k equals to 1 to n, xk, x transpose k, here mx, m transpose x. So the covariance matrix is real and symmetric. So in the second one, find the eigenvalues, and then the eigenvector of the covariance matrix. All eigenvalues arranged in descending order instead of analyze image all eigenvalues. So first find out the matrix. From that matrix all eigenvalues arranged in a descending order instead of analyze image all eigenvalues. Here eigenvalue can be found out using this equation here, cx minus lambda I equals to 0 mod, where cx is the covariance, I is the identity matrix, lambda is the eigenvalue. In this eigenvector can be found out corresponding to each eigenvector. So here c suffix x v1 equals to lambda v1. And third one here, create the transformation matrix T. So find the T or a eigenvector. So from this matrix, from this and so on here, this KL transform matrix T is the orthogonal, that is T minus 1 equal to T transpose. Here T into T transpose equals to 1. So here already I explained this equation, x equals to T into x minus mx. So I explained in previous case y equals to a into x minus mx. So here a transpose equals to a into a transpose x minus mx. Here y a transpose equals to x minus mx. So from this x equals to y a transpose plus mx. Here also x transpose, this is the KL transformation equation. So what are the drawbacks of KL transforms? Here the KL transform is input dependent and the basic function has to be calculated for each single mode on which it operates. So the KL bases have no specific mathematical structure for fast implementations. So in that we need to consider eigen and vector values. So here there is no specific mathematical structure. There is no specific mathematical structure that leads to fast implementations. And the KL transform requires 0 m2 here multiply or add operations. Here discrete Fourier transform and discrete cosine transform is required for log to m multiplications. So this is one drawback in our KL transform. So what are the applications? So for this KL transform, this KL transform is basically used for medical applications, and this is used for compression of an image. In this, basically we are using commonly referred as a principal component analysis, PCA. PCA is nothing but principal component analysis. So with the use of this principal component analysis, we can reduce the data reduction technique is commonly referred as a principal component analysis. Here clustering analysis, the KL transform is used in clustering analysis to determine a new coordinate system for sample data where the largest variance of projection of the data lines on the first axis. So the next largest variance is the second axis, and so on. So because of these axes are orthogonal, this approach allows for reducing the dimensionality of the data set by eliminating those coordinate axes with small variances. So this data reduction technique is basically referred as the principal component analysis. This is the basic application of the KL transform. And second application is image compression. The KL transform is heavily utilized for performance evaluation of compression algorithms. Since it has been proven to be the optimal transform for the compression of an image sequence in the sequence that KL spectrum contains largest number of zero valued coefficients. Here in generally transforms is basically mathematical tool representing a signal. So generally with the use of transformation we are representing the signal only. When we go for in analog means the signal is represented like this. When we are applying the transformation function, the signal one domain can be changed into another domain. So need for transform is given follows mathematical covariance. Every action in time domain will have an impact in the frequency domain. Here convolution in time domain and multiplication in the frequency domain. So first one is convolution time domain can be changed into multiplication in the frequency domain. Here image transform is basically representation of an image. There are two reasons for transforming an image. From one representation to another representation. First, the transformation may isolate. What is the necessity of transformation? So, what is the necessity of transformation means may isolate critical components of the image pattern so that they are directly accessible for analysis. Second, the transformation may place the image data is more compact form so that can be stored and transmitted efficiently. So with the use of transformation, what is the necessity of transformation means first, transformation may isolate the critical components of the image pattern. so that they are directly accessible for analysis. So directly accessible for analysis. And second, the transformation may place the image. After completion of this transformation, that resultant image is more suitable for specific application. In these image transforms, we are having different types. Already discussed those transforms. Just overview of this module. In our second module is image transformation. Just overview of this model here. Here image transforms we are having in four ways: orthogonal sinusoidal basic function, non-sinusoidal orthogonal basic function depending on statistics of signal, input signal, and directional transformation. So in this orthogonal sinusoidal basic function, here it is Fourier transform, discrete cosine transform, discrete sine transform, discrete cosine transform, and discrete sine transform. So in this DCT, in this discrete cosine transform, we are having different types of transforms in our model. Here in image transforms, first one is Walsh transform, and second one is Hadamard transform, and third one is Hart transform, and fourth one is slant transform, and discrete cosine transform, and last one is Kerr transform. In this Walsh transform and discrete cosine, when we go for this orthogonal sinusoidal basic function, we are having discrete cosine transform. In this discrete cosine transform, it consider even number of signals. So here even means when we are going to represent a signal, here in how we can increase the length, of the sequence means here x of n we are representing 1, 2, 3, 4 like this only. Then what will happen? The sequence is extended. The length of the sequence is up to n. So generally sequence is n. How we can extend the sequence? Here extend the sequence means again the same sequence is repeated 1, 2, 3, and 4. What will happen here? This signal to this signal is a drastic change. To overcome this one, we can go for a folding method. So with the use of folding method, we can extend the sequence. That one we are implemented in our discrete cosine transform. In this discrete cosine transform, what is the formula we are using? So what is the formula we are using here? It is x of k equals to summation of k, alpha of k, summation n equals to 0 to n minus 1. Here x of n cos 2n plus 1 pi k by 2n. This is the formula we are using for discrete cosine transform. With the use of this one, we need to consider k equals to 0, k equals to 1, k equals to 2. So depending on length, if n equals to 4, we are using the k value 0, 1, 2, 3. And here if k equals to 0, we need to consider under root of 1 by n. If k value not equals to 0, at that time we need to consider under root of 2 by n. So with the use of this kernel equation, so find out the length of the find out the computations. If capital N equals to 4, we need to calculate total 16. N equals to 4 means here we need to calculate total 4 into 4, total 16 coefficients. We need to calculate total 64 coefficients. So that is discrete cosine transform. When we go for image transforms for non-sinusoidal orthogonal basic function. So these non-sinusoidal orthogonal basic function, in this we are having 4 transforms: Hart transform, Walsh transform, Hadamard transform, and slant transform. Hart transform, Walsh transform, Hadamard, and slant transform. So in this Hart transform, so how we can find the coefficient values? with use of this hard transform. How we can find the Walsh transform? Already completed these all topics: Walsh transform, Hadamard transform, and slant transform. And next one, basic function. Depending on statistics of input signal, basic function depending on statistic of input signal. Here it is KL transform and singular value decomposition, singular value decomposition. And the next one is directional transformation. In this directional transformation, we are having four types: half transform, random transform, and Rigolette transform, and Contourette transform. And here, one of the most powerful transform in our orthogonal sinusoidal basic function is the Fourier transform. Is the Fourier transform. The four transforms whose basic functions are sinusoidal in nature. Whose basic functions are sinusoidal in nature include Fourier transform. So discrete cosine transform and discrete sine transform. Here the transform which is widely used in the field of image compression. So here discrete cosine transform. So here discrete cosine transform is widely used in the field of image compression. With the use of this discrete cosine transform, we can compress the audio and video signals. So this transform is basically used in our image processing. In that image processing, we can use for image compression. So image compression means with the use of this discrete cosine transform, we can compress the audio and video signals. It is used for HD and communication purpose. In this, the transforms whose basic functions are non-sinusoidal in nature includes the basic function is non-sinusoidal in nature, means here the signal we are representing in, here the image we are representing in matrix form. How to find the coefficient value? Here it is non-sinusoidal in nature, includes Hart transform, Walsh transform, Hadamard transform, and slant transform. Here Hart transform is simplest example for wavelet transform. Here wavelet transform not there in our syllabus, but up to here Hart transform, Walsh transform, Hadamard transform, and slant transform, Hart transforms are there. Here the Hart transform is the simplest example of a wavelet transform. So here in Hart transform, how to find the coefficient values? How to find the coefficient values means here in this Hart transform, we are having the characteristic equation. Here the function is defined as hk of z. K equals to 0, any value of z. Any value of z. If k equals to 0, any value of z, k equals to 0, any value of z, whatever the coefficient value, here it is under root of 1 by root 2 only, 1 by root 2 only. If any value of z, for that case we need to consider the characteristic expressions. So what are the characteristic equations to find the coefficient values in our Hart transform means here hk of z equals to 1 by root 2, here 2 power 1 by root n, here 2 power p by 2, here 2 power minus 2 power p by 2. Here 2 power p by 2, here it is q minus 1 by 2 power p less than or equals to z less than or equals to q minus 0.5 by 2 power p. So like this, based on if the z value between this, we need to consider 1 by root n into 2 power p by 2. If z value not between, so we need to consider q minus 0.5 by 2 power p less than or equals to z less than q by 2 power p. So based on these two characteristic expression, we need to calculate the total coefficients if capital N equals to 2 or capital N equals to 4. Capital N equals to 4. Here the transform whole basic the transform whose basic function depends on the statistics of input signal or KL transform and singular value decomposition. So the KL transform is considered to be the best among the all linear transform with respect to the energy compression. So this KL transform is basically used for image compression only. Basically used for image compression, and in this KL transform we need to consider eigen and vector values. So in this image transforms, in this entire model we are having Walsh transform, and second one is Hadamard transform, and next one is Hart transform, and another one is slant transform and DCT KL. Here, when we go for this Walsh transform, what is the kernel equation? What is the kernel equation? G of x comma u equals to 1 by n pi I equals to 0 to n minus 1 minus 1 power b I of x bn minus 1 minus I of u. So remember this formula. With the use of this formula, calculate if n equals to 4 or n equals to 8. Here I value, if n equals to 4 means I value varies from 0 to 3. If n equals to 8, I value varies from 0 to here. If n equals to 4. So depending on that, here I value changes from 0 to n minus 1. So in this case minus 1 power. So minus 1 power capital N equals to 2 power small n. So here what is the value for n? 2 power n means here n equals to 8. So 2 power 3. 2 power 3. Here I value varies from 0 to n minus 1. Here small n minus 1. Small n minus 1 means here 3 minus 1. Here it is 2. I value 0, 1, 2. I value varies from 0, 1, 2. So based on that, calculate if capital N equals to 8 means here small 1 by n pi I equals to 0 to small n minus 1 here. Here it is 8 equals to 2 power 3. Small n value is 3. If length of the here small capital N is nothing but length of the transform, here capital N equals to 8. Then here 2 power 3 means small n value is 3. 3 minus 1 means 2. So I equals to 0 to 3. 0 to 3 means here I value 0, 1, 2. Here minus 1 power b I of x bn minus 1 minus I of u. And when we go for Hart transform, here it is also 1 by n summation I equals to minus 1 power. Here it is 1 by n minus 1 power summation I equals to 0 to n minus 1. Here b I of x b I of u. b I of x b I of u. So what is a shortcut method? For example 0, 1, 0, 0, 1, 1. When we go for Hadamard transform, so multiply b I of x into b I of u. Here b I of x into b I of u minus 1 power plus here also b I of x into b I of u. In this case, what is the I value? In first case, consider I equals to 0. Next, I equals to 1. Next, I equals to 3. So, like that here, first one, 0th bit of x multiplied with the first bit, 0th bit of u. And first bit of x multiplied with first bit of u. Next first bit, second bit of x multiplied with second bit of u. So like that, with the use of this shortcut method also, you can find all the transforms, all the coefficient values For here, when we go for in a Walsh transform, here the shortcut method is 0, 1, 1. For example, 1, 0, 0. For this case, for 0th bit in x multiplied with the second bit in u, and first bit in x multiplied with the first bit in u. Next, second bit in x multiplied with the 0th bit in u. First bit, second bit in x multiplied with 0th bit in u. So like this, calculate the computations of Walsh transform and Hermat transform. In Hart transform with the use of characteristic expression, and when we go for slant transform. So in this slant transform, how to find the slant transform? In this slant transform, we need to consider the constant an and bn. Here an, what is, how to calculate the an and bn values means 3n square by 4 of n square minus 1 whole power 1 by 2. Here bn equals to n square minus 4. Here bn equals to n square minus 4 divided by 4 of n square minus 1 whole power 1 by 2. So with the use of this capital N equals to 4, substitute n value in this equation, and if capital N equals to 8, substitute the values here. Based on these values, substitute in matrix. In our matrix, we are having 1 0 1 0 here, 0th matrix, here also 0th matrix. Already explained this matrix here. an, bn, here it is 0th identity matrix. So based on this matrix, if capital N equals to 4 means here how to find the size of the identity matrix here? Identity matrix n by 2 minus 2. For example, 4 means 4 by 2. 2 minus 2. So identity matrix is 0 only. At that time, rows and columns of the matrix is neglected. Then in our slant matrix, only if capital N equals to 4, here the size of the matrix is 1 0 1 0, an bn minus an bn. Here 0 1 0 minus 1 minus bn an bn an. So substitute the n value, here it is 4. Based on that, here a value we are getting under root of 1 by n, 2 by root 5. An value is 2 by root 5 and bn value is 1 by root 5. Substitute these values and multiply with S2 0 0 S2 matrix. So this is the entire second module, transforms. In this we need to remember what are the properties of 2D transform. So properties of a transformation, we are having most important property is separability, and next one is rotation, convolution, translation, and scaling property. Afterwards, we are having transformations: Walsh transform, Hermat transform, Haar slant in the discrete cosine transform, and KL transforms. So we have to remember properties and transforms. In the transforms, how to write the 1D kernel equation and 2D kernel equation depending on our question. So consider one kernel, 1D kernel equation and 2D kernel equation. Substitute the values, I values or n values in that kernel equation and find the computation values. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.